Last time we started section 3.7 and we had gotten to what I was referring to as a classic optimization problem. Do you remember what we were talking about? A box. It was the box problem. The box is folded up on the edges, and it's problem number 2 in your notes. And so we had written down this formula for volume. We had changed all of the variables into variables with respect to x, which was the corners of the box that were cut apart, right? And we're going to tape them up or something like that to make this an actual box that has volume. And what is it that we were supposed to do? We actually talked about, where we had ended was we talked about these limitations on x. Do you remember how we made those limitations? Whether it would create a box with volume. Really, that was what we looked at. And so, of course, we talked about the fact that if it were a flat piece of paper, there'd be no volume. So the x, the corners, actually have to have something cut out. So x has to be bigger than 0. And it can't be any bigger than 3. And where did we get the 3 from?
So 6, yeah.
It was the side length 6 that we got it from. If we actually cut out 3 inches from both sides, we would end up with a folded piece of paper with no volume as well.
Then
Yeah.
how would you find that if it was given variables for both?
Variables for both what?
Like a different, yeah.
Oh, it wouldn't create an actual box, because if you didn't have the corners being squares, like if one of them was, say, 2 inches and the other one was 1 inch, and you folded it up, you wouldn't have a box of consistent height.
Okay.
And that would create a problem. So the box corners are always going to be squares in order for it to actually create a box. Yes?
If they gave you a problem, they said they made it really hard, like you have to use the ends to fold it over the top to complete the box, would it then be a rectangle?
I mean, it could be. Then you basically would be cutting off something that was you have to have you're saying, so like if it was a 2 inch and a 1 inch and the 2 inch piece folded down to be the 1 inch side. I haven't seen one like that before, but that's a fantastic idea. Maybe we'll use that one as an example. Oh, you didn't want me to do that? Oh, okay. I've never seen a problem written like that. But like in a reality, a real life situation, could that actually happen? Sure. I mean, it could. Yeah.
Might as well do it.
Gus?
That 3 is like saying that having 3 is going to fold it in half.
Exactly. And there'd be no volume for the box. So our goal is to have volume in our box, so it can't be any bigger than 3. Okay, so everybody kind of remember where we were in the setup at this point in the problem? So our length was 10 minus 2x, our width was 6 minus 2x, and our height was x, and we briefly said if we multiplied out, we get this result.
Yes.
Bryson?
Never mind. Question.
Okay. All right, once we have an equation that we're trying to optimize, because we are trying to optimize the volume on this box,
Yes.
what is it that we're supposed to do in our, if you will, our list of guidelines?
Equation equals 0.
Right, we're actually supposed to use calculus to find the extrema. And that means taking derivatives, setting them equal to 0, and solving. So go ahead and take the derivative then of the volume. So what do we get if we take the derivative of v? Okay, I've got mine written backwards of what you're reading, but I've got a 60, I've got a 12x squared, and what else do I have?
Minus 64.
A 64x, right?
Yeah.
All right, and then I'm going to try to set this equal to 0 and solve. You might look at this and see that everything's even at the very least, right? And then you might actually even further notice that they actually are all divisible by 6.
Oh, wait.
And was it 6? Okay, I thought I heard you say 6.
I did say 6.
But it's not 6. 4? Okay. So let's divide them all. If you divided them by 2, you would recognize they're still even. You divide by 2 again. So if we divide them by 4, because this is set equal to 0, so technically if I divide both sides by 4, that doesn't actually change the equality. So if I divide 60 by 4, I get 15. 64 by 4 is 16x, and then I've got the 12x squared, which becomes 3x squared. And I know some of you already have them in order of decreasing exponent, which is going to be helpful, so let me rewrite mine as well. And they're equal to 0. Now, it would be absolutely fantastically wonderful, and we would all feel good in our hearts and our minds if this factored. But it doesn't. And if you try, that's cool, and you can see that it won't pretty quickly. You're going to run into some problems. So we are going to have to use either completing the square, the quadratic formula, and I've never had a class tell me before, completing the square, let's do it that way. I've never heard that. So probably we're doing quadratic formula, right?
Yes.
Okay. All right, quadratic formula. Do y'all remember the quadratic formula? That's a fantastic question.
B plus or minus square root of b squared minus
two teacher had a song.
Yeah.
Yeah, we do have, yeah.
There is a
Can
song.
we have a song?
Okay, let's take a look at a couple of common mistakes people make, even if you read this out right to me out loud that I see.
Yes.
Pay attention, guys. That square root needs to go over the b squared all the way to the 4ac, so make sure that square root looks like it goes all the way across. The division needs to be under everything in the numerator. Sometimes I see people write the division, they only write it underneath the radical part of it, either because they really think that's true or because they're just not being careful. So be very careful that your pieces are all in there. And the function we had from the previous slide was 3x squared plus 15x. It was all addition, wasn't it? No, it was subtraction, I'm sorry. Minus 15x and plus 16 equals 0, right?
I thought it 16x.
Do I have my 16 and my 15 in the wrong place? I do. I'm sorry. Let me get those in the right spot. 16x plus 15. Okay, is that all good? All right, so this one is A. This one with its sign is B. And this one is C. So x equals negative b, but our b is already negative, so this will be a positive 16, plus or minus the square root of b squared. Well, that's negative 16 squared, but when you square a negative, it's also positive, so that's actually the same as 16 squared. Minus 4 times a is 3 and c is 15. All over 6. So, for the sake of clarity, go ahead and find out what is 16 squared minus 4 times 3 times 15. It's 76. Okay. I had several of you say 76, so that must be right. That's actually not the way real life works, but I hope that it's right since several of you said it. Is that right? Okay, good deal. We're going to get 2 answers out of this, right?
Yes.
Because one of them is going to be the 16 plus and the other one's going to be the 16 minus. So go ahead and find out what is the 76 approximately. Let's actually write that in first. What is it? 8.7178. And if we keep lots of decimals and only round at the end, that's really our best bet at keeping things accurate. So I need a 16 plus that value. Hit enter, divide by 6, and what do I get?
4.1196.
Okay, and we'll go with 2 decimals. So if we do 2 decimals, Fallon, what does that give us?
4.12.
Okay, and then let's do 16 minus this. And these are approximations, of course, because we're rounding. 1.21. Does everybody have those 2 values? Now, general rule of thumb, we like to keep things in radicals. WebAssign expects you to keep them in radicals. I expect them to keep in radicals. Why on this problem am I not expecting radicals?
If the box
Katie.
is practical, it's real.
Because in a real life situation, you don't deal with radicals.
Right. Yeah, if we're really cutting the sides of the box, we would grab a ruler and we'd do some sort of a measurement, right? And if we were doing that, we would use decimals to do the measurement for it. So decimals make sense in a real life context, and several of you were saying that. Now, are we really going to have 2 answers here?
No.
Which one's not okay?
The 4.12.
4.
Yeah, and why not?
It's big.
Yeah, it was bigger than the 3 that we established as our sort of our maximum point before. Now, we believe then that 1.21 inches is our answer. But what we really just found is that it's a critical point. We didn't really find out that it maximizes the volume, correct? So how do we decide if it maximizes the volume? Either the second derivative and plug it in, or what's our second option? A number line and look at the first derivative. Which one would you guys like to do?
Number line.
Number line. For some reason, people like to do number line. This one would work really nicely for a second derivative, just so that you're aware, because this function is really clean. It's polynomial. So if you want to do it as a second derivative on this one, that would make a lot of sense on this particular function. Most of you, however, said number line, so I'll do a number line.
Can we do both, actually?
Sure. Yeah, no problem. All right, so if we do a number line 1.21, we need to test a value on either side, but it still needs to be between 0 and 3, right?
Yes.
Okay, so what number did you want to test, Chad? 1 and 2. Those sound like good values to test. What are we going to test them in?
Regular function.
The first derivative. First derivative.
Why is that?
Because the first derivative tells us where a graph is increasing and decreasing, which is what we're trying to find out.
Okay.
Increasing and decreasing will give us the information for max and min. So what happens in terms of the sign if I plug in the number 1 into the first derivative? Okay. And into the first derivative, I plug in 2, a negative. So in terms of my picture, I'm going increasing here, I'm decreasing here, so what happens up here?
Max.
That is a max, and this is the calculus verification that we really checked it out, and it's really a max. So our answer is in fact the 1.21 inches. Okay, it said to find the value of x that maximizes the volume of the box. Do you have a question, Dawson?
What if that was a min? And we're wrong somehow?
Then one of the endpoints would be your max.
Okay.
Yeah. And of course that doesn't make sense on this particular problem because the endpoints give us no volume at all, right? Okay, so the other one then, if we did the second derivative. So let's do the second derivative of this. So let me write down our first derivative first just to remind us where we were. I had on my previous slide 60 minus 64x plus 12x squared. You could use the value, the same one that we did when we divided it by the 4. It'd be okay. It wouldn't change anything. But most of us probably wouldn't think to use that one, so I'm going to use the other one. Okay. So the second derivative then, with the 60 becomes 0. This becomes negative 64 plus 24x. Right? We don't set it equal to 0 because we're not concerned about the concavity. Setting it equal to 0 gives us information about concavity and points of inflections. We just plug in the critical point, the 1.21 into this.
Okay.
And what we want to know is we want to know if that gives us a positive value or negative value. So what do we get when we plug in the first, or the 1.21 into the second derivative?
Negative.
It's negative. What does negative mean for second derivative?
Concave.
Concave down. And if a graph is concave down, what does it have?
Max.
It has a maximum. So one of these two pieces of information, either this or this, needs to be present to verify. You don't need both, but one of them needs to be present to verify that you do in fact have a max.
Okay. Question real quick.
Yes.
On the number line, do you plug it into the first derivative or into the original?
Yes, this is first derivative. See the notation down here?
Yeah.
Yes, it's first derivative.
You don't just have to use inflection points for the second derivative, but you can use critical points.
Well, the second derivative, if you set it equal to 0, will give you potential inflection points. But that's not what we're wanting to find here. We're wanting to find maximums and minimums, so we don't set the second derivative equal to 0. Right. We're plugging in the critical point into, and that's called the second derivative test. So what we do over here, this is the first derivative test. And what we did up here, this is the second derivative test. But the tests both tell us information about whether a function is a max or a min. That's something you probably should write down about 10 times on your paper, before you go take your test to remind yourself, because if I ask you to use the second derivative test and you use the first derivative test, that's kind of a problem, right? Or if I ask you to use the second derivative test and you start telling me about concavity, that's a problem. That's not what the second derivative test talks about.
There's not anything we have to memorize for this.
Nope, there's not. Okay, last question. You guys ready for it? Okay, this one's a bit more mathematical, not application. This is a bit less application material, okay? Still really applicable, it's fine and everything, but it looks a little bit more mathy. The last ones look like, oh my goodness, I have a piece of paper and I'm cutting corners out of it. Like that makes more. And the other one was a perimeter of a rectangle alongside of a river. I mean, you can see the real application. This one looks less like that. So we're going to find the point on the curve y equal x squared that is closest to the point 0, 1. And just like we did on the other examples, a picture will help us to kind of get our minds wrapped around what's going on here. So I've got the graph of y equal x squared, which looks like a what? Yeah, it's parabola or a U shape. And it's opening upward, it's symmetric around the y-axis, and it looks something like that. It's not too bad. It talks about taking this curve and getting really close to the point 0, 1. Well, 0, 1 is here. Now, one of the things that we have done as we've looked at other problems is we have said what a maximum or minimum value would be. So if you went straight down, how far apart are those 2 points?
1.
It's 1. So it's actually the distance. We know that the distance minimum has to be less than 1 because I can go straight down and get to 1. Not only can I go straight down and get to 1, it's the same thing if I go to the right. Also 1, right? So
Yeah.
I'm thinking that my answer should be somewhere in between here, right?
Yes.
So I'm expecting my x value to be between 0 and 1. Yes.
What about the other side?
Same thing. We're going to get two values. We're going to get a symmetric picture. So whatever we get for x, we're going to get the positive and the negative value of it. Yep. We expect to get 2 points. Okay, I put d minimum as distance, d for distance. That's what I was writing. So I expect that the minimum distance should be less than 1, because I know I can get it to be equal to 1. The question is whether I can get it to be less than 1. And you might have the feeling, and you probably should, that if I went across here somehow, somewhere, it would be less than 1. Don't you? And it will. So the key is, though, that we're trying to find the closest point on a curve. So what is there we're looking for?
Curve.
We're looking for a minimum. That's good. And we're looking for the distance, right? Do you remember a formula for distance? The distance formula. Do you remember what it is, Garrett?
D equals A.
Not really. This is square root.
It is a square root. Good job.
x2 minus x1 squared plus y2 minus y1 squared.
Way to go.
Well done. And if you haven't already sort of thought about this before, really what this is it's a Pythagorean theorem.
It is.
If you square both sides, you've got the Pythagorean theorem here. Kind of cool stuff. A squared plus b squared equals c squared. It's just a different version of it. So you're finding the hypotenuse, if you will, of a triangle. If that blew your mind, then we can talk more later. But at any rate, some of these pieces of information you know, and some of the pieces you don't know. So I've got x2, x1, y2, y1. I can't have 4 variables, and that's what I have right now on the right-hand side, correct?
Yeah.
I'm supposed to have 1 variable. So what is it that I know from the information that I was given in the problem?
0,
I know 0.01. So 0, is that x or y? That's x. So right now, I've sort of simplified this down to x2. And since it's just x2, can I just call it x now? Are you guys good with that? So this is like x minus 0 squared, or just x squared. And then I know that my y value that you just told me was 1, right? So this is now just one y value minus 1 squared. Make sure your square root goes over everything again, too.
Okay.
I still got 2 variables, though. I've got an x and a y.
Can we just plug it in x squared? So
Yes. There's a formula that relates the two together, right? This curve has the equation x or y equals x squared.
Yes.
So I can replace the y with
X squared.
x squared. So now I've got x squared here, plus, and I have x squared minus 1 squared here. Because y is, in fact, x squared. Because that's the equation I was given. If the equation you were given was something else, that's what you would plug in there.
Why does the x minus 0 squared just go to x squared?
Because x minus 0 is x.
Oh, okay.
Yeah, I just
I thought you were
simplified
trying
the
to plug in
expression.
x squared still.
Nope. Just simplified it.
Cool.
Now, before we go getting all crazy here, it's going to help us a lot if we really just simplify this before we take a derivative. That is, if we multiply the x squared minus 1 out. And if you tell me that that is x to the 4th minus 1, I might put like something up here that says, ah! I've done that before.
X to the 4th minus 2x
Okay.
squared.
Because this is foiling, right? You cannot distribute squares. That is a complete fallacy. Okay? So we have to simplify that with foiling. So this is x squared. Luke, what did you want to tell me next? So we've got x to the 4th, and then minus 2x squared, and plus 1. So if we multiply first, outer, inner, last, yes.
Can we just like make it x, the square root of x squared plus the square root of x squared minus 1 squared? And then like
Okay, so what you're basically asking me is if the square root of 25 is the same thing as the square root of 9 plus the square root of 16. Is it? No. You cannot square root pieces of something because it's the same as trying to distribute x squared, or trying to distribute the squares. It's not a valid operation. So no distributing square roots, no distributing squares. Absolutely not allowed.
And you couldn't just like, why doesn't it just make the squares go away? Is it the same as
Well, what is the square root of 9?
the 3,
What is the square root of 16? What's the square root of 25? And these are not equal, right? But that's exactly what you'd be trying to do and trying to say worked if you're doing what you're suggesting, which is to square root each individual piece. It doesn't work. Now, there is a variation of this that does work, and it's with multiplication. So let's say, for instance, you had the square root of 400 underneath here, and you weren't sure what to do. Well, you could change that to being the square root of 4 times the square root of 100. It works when it's multiplication underneath the radical, just fine. It does not work if there's addition or subtraction. Okay? Division would work too. Yeah, multiplication and division are really the same thing. We just act like they're different. Yeah. Okay, is everybody okay with this at this point?
Yes.
So we're not going to distribute squares and we're not going to distribute square roots, right? Okay. I can combine these and simplify this a little bit. I've got an x to the 4th, and I have a minus x squared now and a plus 1.
Cool.
Does that look okay? All right. I have one variable. I have the equation that I'm supposed to be minimizing, the distance equation at this point. So what am I ready to do?
Plug it in.
Take the derivative. I'm ready to do calculus. I haven't done any calculus yet, right?
Why B? It was D.
Oh, I'm sorry. It was D. Thank you. All right, so what is the derivative of this equation?
1 half, all that stuff.
X to the 4th minus x squared plus 1. All
So
over
negative 1 half times 4x cubed
All
over
that could
2x.
4x.
Looks pretty good. Do I have a second and a third and we're all okay? Cool. All right, if I clean this up a little bit, and we are going to do that.
Okay. 2x minus x.
The part that's to the negative exponent will go in the denominator, right?
Yeah. 2 will cancel.
And there will be a 2 that cancels. Good observation. So I'm going to have a 4x cubed minus 2x on top. I technically have this 2 on bottom, and I have a square root of x to the 4th minus x squared plus 1 on bottom. And this 4, 2, and 2 are able to reduce. So I have 2x cubed minus x over the square root of x to the 4th, whoops, minus x squared plus 1. Okay, I've got the derivative. It's as clean a form as I'm really going to be able to get to. Now what? Okay, I need to set it equal to 0. Now, this is only going to be equal to 0 when what part is equal to 0? The numerator. So the denominator equal to 0 is a place where it doesn't exist, and that's something we need to check out, right? But the numerator equal to 0 is going to give me the equal to 0 part. So now we've got this piece, and then the denominator equal to 0 will mean that the x to the 4th minus x squared plus 1 would be equal to 0, so we'll check that out in a second here. What about this numerator, though?
You can simplify x, pull out the x out of it.
Good. We're going to factor, right? We're going to factor the x out. That gives me 2x squared minus 1 equals 0. Now what?
1 half squared is
Each piece equal to 0. The first one is x equals 0. The second one is 2x squared minus 1 equals 0. So let's do the second piece.
square root of 2 divided by 2.
Okay, so I'm going to add 1 and divide by 2, right? So this is x squared equals 1 half.
Okay.
And then take the square root. And when I put a square root into a function, what do I have to remember to do?
It's for both of numerator and
Plus or minus.
Plus or minus is what I was going for. It is for the numerator and denominator, you're right. But the plus or minus is the part that I was wanting to remind you of. And that goes back to Dawson's question originally of what about the other side of my graph, right? I'm going to get a value on both sides. So do you know what the square root of 1 half is written differently?
square root of 2 divided by 2.
Have you seen that value before?
Square root of 2, yeah, sine.
Unit circle, that's right. Do you remember where it shows up on a unit circle? Pi over 4 or 45-degree angles. So does that make sense when you're thinking about this graph that there is a 45-degree angle right here and right here?
Yeah.
Yeah, it makes sense, right? Is your mind blown, Bryson? You're just like, wow, oh my goodness, that there wasn't even any trig in the problem, and she brought trig into the problem. That was crazy. What?
I thought that's the farthest distance. 45
It-
degree angle, when you draw it, punch it, is like longest distance.
But that's because it's doing an arc. When you're talking about throwing something, we're not throwing in an arc. We're finding distance as the crow flies, straight line segments. So, Okay, let's just make sure there's nothing else going on with this x to the fourth minus x squared plus 1.
Do we still have to do
Does that ever equal 0? I don't even think I have this part written down. No? It never equals 0? Fantastic. I'm going to go with you guys on that one. So this one is always going to give me nothing.
Do I have to write it down?
We're trying to find out whether x to the fourth minus x squared plus 1 equals 0.
Do you
So
want us to do that test or just ignore it? Because we've been ignoring it since the chapter started.
we've been ignoring the denominator, you
Yeah, 'cause
mean?
it will go to
There are
infinity.
times when that denominator equaling 0 could be a value that we would need. It could be an asymptote, but this one wouldn't have to because it's a radical. The radical part could give you something that looks like that.
True.
So you have to be a little bit careful.
Yeah.
Okay,
I have a question.
yes.
Is the x equals 0 still applicable?
Good question. The kicker, though, is that we know what the distance is when x equals 0, don't we?
Yes.
It's 1. We know that distance is 1, and we were already looking at values that were sort of between and not that value. So if we can find a distance that's actually less than the value 1, the distance value, then we're actually, that's not going to be our answer. Yeah.
So if you had like a different equation and you found the other two values were bigger than 1, you would just automatically know that 0 is your answer.
Bear with me for one more second, because we're going to do a number line, because I don't think we really want to do a second derivative on this one. Are you guys agree with that?
Who does?
This is not a polynomial, so I would probably not do a second derivative. Let's do a number line. And on our number line, we are going to have all three of these values. Like that. And we don't need to go out any further than 1, right?
Yes.
All right, so I do need you guys to figure out for me, though, what approximately decimal-wise is the square root of 2 over 2.
But everything is possible.
Okay, so I need values, this is going to be about 0.7, right? I need values that are between 0.7 and 0, and then between -1 and 0.7.
0.8.
Okay, 0.8. What else? 1/2, 0.5, okay. And how about we use the same values, just positives? Is that good with that?
Yes.
Okay, so these are my 4 values I'm going to check. Into which function?
First derivative.
The first derivative. So, whoops, we called that d. So we're doing d prime of 0.8, or -0.8, d prime of -0.5, d prime of 0.5, and d prime of 0.8. And my suggestion would be to take this version of it right here and put it into y1, and then use your table, because you're going to enter it 4 times.
Yeah.
You don't have to do it that way, but that would be what I would do.
Sounds good.
I have a question.
Yes.
If the function was radical, like x minus 3, and you have to reach like certain height like that, would you do the same exact thing?
Bless you.
Yes, the process would be the same. Your place where you plugged in y equal x squared would look different. You'd have y equals square root of x minus 3 or whatever.
So the first part, though, using Pythagorean Theorem, which is distance formula.
Yeah, that would be the same.
So, and we put x and y as a just like value we're looking for.
Yeah, this is the place where your function's equation itself came into play.
I'm just a little confused because the x and y just still there. So those are the variable we're looking for. Is that
Well,
what it is?
our function only has x in it. It's only the distance in x.
No, the first part, like how we know it's x minus 0 and x minus
Uh-huh. Yeah, this is always the same.
Okay.
The only place where it changed things was right here where we plugged in what x and y are actually equal to in the relationship of the function we were given.
No, like x minus 0. Like how we know it's x.
Because they gave us the point 0, 1.
Okay. And
So
we
whatever
don't have
point
other-
we gave you would have that information in
We
it.
have other points. That's why we just keep x and y. Is that why?
We'd only have 1 point and we have 1 curve.
Okay.
So the point 0, 1 went in because that's one of our ordered pairs. The other ordered pair is the one we're looking for.
Okay.
We're looking for the x and the y to make this true.
Okay.
So they go in as x and y.
Makes
So it's really kind of like we have 2 points. One point is 0, 1. The other point is x, y.
Okay.
So these are the 2 points that we're using.
Thank you.
Yeah. Yes, Dawson.
Okay, so plug in the 4 things to the calculator.
Yeah, do you have them?
Yeah.
Okay, what'd you get? Signs.
0.25,
So you got negative.
positive, negative, positive.
Okay, did everybody get those?
So you don't even need to put like
Numbers.
I'll ask you for positive.
Okay. It's only the sign that we care about, because the sign tells us whether it's decreasing or increasing. Negative means it's decreasing. Positive means it's increasing. Negative means it's decreasing. Positive, increasing.
Decreasing and increasing intervals with this.
We don't have to, because we're answering whatever question's being asked.
Okay.
So our concern about this one is to find the point that gives us the information we are concerned about. So right here, is this a max or a min?
Minimum.
Minimum.
We want minimum distance.
Notice what happens at 0.
It's a max.
It's a max.
It's close.
So Fallon, that's what I was telling you about. 1 is the maximum on the interval we're looking at anyway, right? It's a relative max. And what happens over here at the positive square root 2 over 2? It's another minimum. Now there is one catch on this problem. It asks for the point on the curve,
There's 2.
and there are 2 points, and these are the which values?
Closest to 0, 1, though, so it's.
Okay, they're the x values where you're closest. So this is negative square root 2 over 2, and this is positive square root 2 over 2, but we're asked for the points, which is an ordered pair,
Yeah.
right?
So you have to plug it.
Yeah, so we have to plug them in. So what do we get for the y value then when I plug in? I mean, the relationship is what I'm plugging them into here, right? If x is square root 2 over 2, what's y?
1/2.
It's 1/2. And it might be easier, even if you're thinking about it, to remember where it came from before I rationalized. It was the square root of 1/2, right?
Special triangle.
Yeah, so when you square the square root of 1/2, you get 1/2. So we have 2 closest points, quote unquote. They are the square root 2 over 2, 1/2, and the negative square root 2 over 2, 1/2. 2 ordered pair points. There's a lot of work on that one, isn't it? And the radicals in there make it really messy.
And we
Yeah.
do have Wales on homework. That was about